So Hemant, could you please explain about this particular device?
Yes. This is a rectangular pyramidal horn antenna, and the main part of this horn antenna is this waveguide.
Yeah.
This is a rectangular waveguide.
Okay.
Have a dimensions of 50 mm by 120 mm.
Okay.
And the length of this waveguide is 110 mm.
Okay.
And this is fed using a coaxial connector.
So this part is the coaxial connector.
Yes, this is a coaxial connector, and we can see inside this we have fed using a probe.
Yep.
This one.
Okay.
And this probe have a length of around lambda by 4.
Okay.
So it's working as a lambda by 4 monopole antenna.
Okay.
And the aperture part is this length of this aperture. You can say as a width.
Yeah.
Wider dimension of the aperture is around 450 mm.
Okay.
And the narrower aperture dimension is 320 mm.
Okay.
And the length of this flaring,
the flaring
total
part,
is so it's a 250 mm.
Okay.
And the length of this waveguide is 110 mm.
Okay.
So the total length of this antenna is 360 mm.
Okay. Okay. This is mainly used as a reference antenna.
Yes, this is mainly used as a reference antenna for GSM and CDMA band.
Okay.
So to measure the radiation pattern and gain of any other antenna,
Yeah.
we can use this as a reference antenna.
Okay. And I know that you have also simulated this antennas
Yes.
using some simulation tools.
We have used various simulation tools, and we have simulated and verified the results.
Could you please show us some of your simulation
Yes,
results?
sure, sir.
Okay. So Hemant, so what you have basically showed us is the physical horn antenna.
Yes, sir.
So what you have done here is, if I understood correctly, you have taken the physical dimension of the horn antenna.
Yes,
You have put into a simulation tool with
Yes.
all the dimensions in.
Yes, sir.
And you explained me the feeding is going to be very critical. So could you
Yes.
zoom it in and show us?
Yes. This is a coaxial connector.
Yeah.
And inside this we can see there is a probe.
Okay.
This one.
Okay.
And the length of this probe is around lambda by 4 at
Yeah.
the frequency of operation, around 850 megahertz. So this is very important how to feed the antenna.
So I think the discretization around that part is going to be very critical.
Very,
So
yes.
is it possible to also see the discretization?
Yes, we can show this discretization. We can see like this.
Okay.
This is
Could you zoom it out, zoom it in a little bit?
Yes, sure.
So this is the entire flaring region.
Yes, sir.
So when we see the small areas, it's very finely
This is-
discretized.
Yes.
And you have a tetrahedral mesh and
Yes.
also a rectangular mesh.
Rectangle.
Okay. So could you zoom it out a little bit and show us a little bit on the waveguide side?
Yes.
So excellent. So have the results of the simulation are comparable to
Yes,
the,
sir.
okay.
That is comparable.
So could you show us a little bit on the results?
Yes, sir. Results, first we always talk about the S parameters, the reflection coefficient, and that can be seen from here 1D results S11, and we can see the S parameters are below 10 dB, minus 10 dB, from 700 to around 1130 megahertz.
Okay.
So, and the maximum, you can see the peak is at 850 megahertz, around minus 39 dB.
Okay.
And the gain for this antenna, you can see this is varying from 8.4 dBi to around 12.5 dBi.
Okay.
Over the
So
frequency range.
the main idea of simulation, the computational simulation, is to get a reasonable idea about what is the S11 parameter is going to
Yes.
be, and also the gain is going to be.
Because we are going to measure the radiation pattern and gain of other antennas, so we're making a reference antenna.
Okay. So the idea of this particular simulation is to get a good understanding of the
Good.
reference antenna.
Yes, yes.
So that the other antennas which are basically measured based on this will be more
Yes.
accurately
I
done.
can also show you the i3D simulation for the same. This can be, yeah.
So
This
could
is
you-
the meshing view.
So
there.
could we look at the different dimensions of?
Yes. So I am showing you the 3D geometry for this.
Yeah.
So in 3D geometry, we can see the dimensions of this waveguide.
Yeah.
This width is 240 mm.
Yeah.
And this height is 120 mm.
Okay.
So it have a lower cutoff frequency around 600 megahertz. So there is no attenuation of our working frequency. So in the length of this waveguide is optimized to 110 mm.
Okay.
And the flaring we have done this width. This wider dimension of the aperture is 450 mm.
Okay.
And the narrower aperture is 320 mm.
Okay.
And the length length of this horn is around 250 mm, and we can see the gain of this antenna is varying from 8.4 dB to around 12.5 dB.
Excellent.
So these are the main results.
So these are the main things. So the main idea of simulating this reference antenna is you're going to use this antenna as the basis for evaluating other antennas. So in that sense, the gain and also the S11 parameters.
GSM 896 and the CDMA band is.
Okay. Thanks a lot, Hemant.
Thanks.
We are in the antennas lab, which is one of the most important labs in the microwave engineering, where we simulate various kind of antennas. And today we are going to look into a special type of antenna, which we call it as patch antenna. So why we call it patch antenna is because we have a kind of a metal layer which is sitting on a dielectric. So in this case, we are using a FR4 substrate, which is fire retardant substrate with dielectric permittivity, which is roughly 4. And then we are also having another material, which is Arlon, which is with relative permittivity of 2.55. So we are going to simulate this particular kind of antenna using a method called as method of moments. And the reason why we are going for method of moments particularly is because the phenomenon which we are interested in this kind of model are the surface phenomenon. So we are not going to discretize the volume, we are only going to focus on the surface aspect. So that way we can get the best result in terms of accuracy and computational time. And one of the students here is going to help us model this kind of antenna using the method of moment solver. And we are going to use a IE3D solver. And let's hear from him how he is going to go from the physical model to the model which is going to build on the virtual platform, and we'll see what are the results that we are going to look into and how this entire project can be done using IE3D. So let's go and have a discussion with the student. So Hemant, so you've been working on this particular kind of antenna.
Yes.
And so could you please explain us what you're doing on your solver and explain us how you are going from the physical model, what is the problem that you're going to solve, and I know that you have a PowerPoint presentation where you have explained step by step what you have done. So could you please explain us?
So,
okay. So this is a microstrip patch antenna simulation.
yes.
And we are doing this as part of the computational electromagnetics and application course. So could you please explain what you have done?
Yes. We have taken a patch antenna.
Yeah.
This one is a patch antenna.
Yeah.
And this is a ground.
Okay.
So from here we can say this is a ground layer.
Okay.
This green part.
Okay.
And this is a patch.
Okay.
The
So
top
you
layer.
basically have
Yes.
a kind of a metal layer which is on the bottom of the dielectric, which
Yes, sir.
acts as the ground.
Yes, sir.
And then you have on the top the patch antenna itself.
Yes.
Okay.
So this antenna is working at 2.03 gigahertz.
Okay.
So using the formulas available in the literature, we have found that L equal to W equal to 45 mm.
So basically you're starting with the length which is
and
equal to the width.
W.
So it's a kind of a square.
microstrip patch antenna.
Okay, okay.
And the feed point is decided based on the input impedance.
Okay.
Means if we are, we can simulate it in I3D, and we can see as we are moving the feed point away from the center, the impedance will shift towards the higher value.
Okay.
So
okay.
from center we will have to optimize this feed point at a point where we are getting 50 ohm impedance, because we are going to feed it a coaxial feed. So the coaxial feed have an input impedance of 50 ohm.
Okay.
So to match the input impedance with the coaxial feed SMA connector,
Okay.
we have to shift. We have to optimize this.
So basically, we have the basic sourcing is coming from the coaxial feed. And the impedance for that particular coaxial feed is a 50 ohm resistance. And now what we are doing is we are trying to match it in such a way that whatever energy is getting fed doesn't get reflected. So maximum energy transfer is happening.
We have to go to minimize the reflections.
Okay, so that's the reason for matching the impedance.
Yes.
So you have basically used the kind of a simulation to find out where the position will be appropriate for you to match it for the input impedance of 50 ohms.
Yes.
Excellent. Okay.
So we can show you, this is a SMA connector.
Okay, so this is a SME connector.
Yes.
And
so this point is in the inner conductor of the SMA coaxial cable.
Okay.
And you can see a white here, middle layer.
Okay.
This is a Teflon layer.
Okay.
And the outer is again metal.
Okay.
So outer is connected to the metal bottom ground layer.
Okay.
Metal, and the inner is connected to our patch antenna.
Okay. Okay.
So
basically you have a Teflon layer that is
yes.
also insulating between
yes.
the
yes.
bottom layer and the top layer.
Yes.
So it's kind of coming from inside, and
yes.
then this point is exactly matched so that the input
yes.
impedance
is
and
50.
the impedance is 50 ohms.
Yes.
And what kind of a connector is this one?
SMA connector.
SMA connector. Okay. So could you please go forward and then explain us further? So what are these X and
X is the distance from center to the feed point.
Okay, so the X actual,
yes.
so you're basically modeling it as a 2D problem.
Yes, 2D.
So you are taking the X axis as this axis and Y axis as this axis. So now
this is our X axis. This is our Y.
So this is your X axis and this is your Y axis, and you're trying to compute from the center what is this particular distance, and this is equal to
7.3 mm.
Okay.
And this is the dielectric constant of our material.
So you have
this one is our Arlon material. This is our FR4 substrate. So we have done analysis for different substrates.
So basically for this Arlon material, you have taken this X is 7.3.
Yes.
So this is in centimeter or millimeter?
Mm.
So this is in millimeter,
yes.
And you are talking about epsilon r of 2.55. And what is this tan delta?
This is the lowest tangent of the substrate.
Okay.
It is very less, 0.0015.
So these are computed based on basic
and the thickness of this substrate is H 1.6.
So this is 1.6 mm.
Yes.
Okay, so then can you go forward?
Now we can show you the simulation.
So first show us how you are doing the entire model.
Okay.
From the physical model to the virtual model.
Okay. So here is M-grid we have opened.
So M-grid is basically a kind of a geometrical design platform.
Yes. So we are going to open a new file. We are going to design. So we have two layers.
Okay.
One is a ground. We can see here Z top is 0.
Yeah.
Means it is a ground.
Yeah.
And the sigma is infinite. Means it have an infinite conductivity.
Okay.
So and above layer is D, that is at infinite.
Okay.
This 1e 10 to power 15 is
so it's a very high value.
Very high value. So it is treated as infinity.
Okay.
So we have to make a patch at a distance, so at a height of 1.6 mm.
Exactly.
So we have to insert one layer at a distance of 1.6 mm.
So this is the dielectric.
So Z top should be at 1.6 mm.
Yeah.
And the epsilon should be
2.55.
our substrate 2.55.
Okay.
And the tan delta is the lowest tangent of the substrate is 0.0015.
Okay.
And permeability is 1, and all the other things we are not going to change. Then press OK. So we can see a new layer is inside.
Okay.
And as this layer is where in I3D basically this sigma is infinity, means the bottom layer is infinite long.
Yeah.
So we have to finite it, means we are taking a finite ground plane size.
Okay.
So we have to also make it a year.
Okay.
Because sigma is infinite for a conductor and 0 for air.
Yeah.
So we are going to make it 0.
Okay.
So there is no conductor at bottom.
Okay.
At this time. Then press OK.
Yeah.
So we have a new window, editing window.
Yeah.
We will design our patch antenna in this window.
Okay.
So firstly we have to design a square patch antenna.
Yeah.
So we will select this rectangle.
Yeah.
Click on this and we can see X coordinate, Y coordinate, Z coordinate. Z coordinate, we have to design a patch antenna at a distance at a height of 1.6
mm.
So Z is 1.6.
Yeah.
X coordinate, Y coordinate, we can take any value, 0.
Okay.
0 is, by default we are taking 0, 0, so that it will become at a center of the X and Y axis. So the length of this antenna is 45 mm. We have entered 45. We have already calculated it. Yes. And width is also 45 mm. Then we will press OK.
Okay.
So this is a patch.
Excellent.
At a distance of 1.6 mm.
So what we are seeing now is the entire patch, but this is the ground plane or on the top?
It is at a height of 1.6. There is no ground plane.
Okay.
Right
so
now.
far now there is no ground plane.
We have to make it by again selecting a rectangle.
Yeah.
Now this time we will take z coordinate equal to 0
because
we
it's
have
at
to,
the lower level.
yes.
Okay.
So we will 0, and generally we take a ground plane
Which is larger.
yes, larger than the patch size.
Okay.
So it has been observed that if you take a finite ground plane of a size 12h greater than a patch antenna size, means
Yeah.
if the patch length is L and we are taking a finite ground plane length equal to patch length plus 12h.
Okay.
So h is a thickness of our
Okay. So in this case, how much you are going to
so
choose?
we are going to choose 45 mm
Okay.
plus 12 into 1.6.
Okay.
It's around 18 mm.
Okay.
So we can take around 64 or
So the
64.
ground plane dimensions are going to depend on the dielectric thickness itself.
yes.
So the thicker the dielectric, you are going to have a bigger patch. The thinner the
These are
dielectric.
the observations.
Okay. Okay.
So we are going to take a 64.
Okay.
And the z is 0
Okay.
because
Okay.
it
We
is
are
at a
okay.
0.
Okay.
So this bigger scale is finite ground.
Yeah.
So we can see this is a finite ground.
Yeah.
So when we select our 1.6, this is our patch antenna.
Okay. So this is exactly this one. What
This
we have.
one, yes.
And now
we are going to feed it.
Yeah.
There are various ways to feed a microstrip patch antenna.
Yeah.
Like microstrip line feed,
Exactly.
inset feed,
Yeah.
coaxial feed, aperture coupled
Yeah.
feed.
Yeah.
But in this, and all these have different have advantages, disadvantages. But we are going to use a
Coaxial feed.
So here to feed this antenna, we are going to use coaxial feed.
Yeah.
We'll go to the entity. There is a pro feed to patch.
Yeah.
So
This is for this.
yes, this
particular-
connector we are going to use, the
Yeah.
SM connector. Its inner dia is 1.2 mm.
Okay.
So we can see a new window is appeared.
Yeah.
Pro feed to patch.
So there
Here
you
X
can give-
and Y. X and Y will decide the position or the location of the feed.
So we said that
So
it's
we have
7.6 mm.
7.3 mm.
Yeah.
So X is 7.3 mm and Y is 0. So we will have to enter
Enter.
it. So at 7.3 there will be a
kind of feed that will be.
so
inside.
number of segments for the circle can generally taken as a 16,
Yeah.
but it depends. Means we cannot make a perfect circle.
Yeah.
So to make a circle in a simulation, we
Yeah.
generally take 16 segments.
Yeah.
So if you take a 4 segment, it will become a square.
Yeah.
Like that.
Okay.
So we are taking it 16 circles.
Okay.
16 segments, and the start z coordinate.
Yeah.
Start z coordinates will tells us this.
Particular thing. Okay, this is. Okay.
So it should be 0.
okay.
Here. And z coordinate is 1.6 mm because we are going to feed the patch at a distance of 1.6 from the ground.
Exactly.
So and this radius,
Yeah.
this radius decides the inner dia.
It's the inner dia of the
So
particular
inner
feed.
dia is 1.2 mm means
Yeah.
radius is 0.6 mm.
Exactly.
0.6, and now you can see press OK. There is a
So you're basically getting this particular
Yes.
area
Yeah.
where the feed is coming in,
feed coming.
and this is 7.6,
This is 7.3.
7.3 mm from the
From the
center,
center.
and 0 from the center. So it's exactly on the y equal to 0 line,
Yes.
and 7.3
On
mm
the
away
axis.
from the
Yes.
center.
And we can see the 3D geometry.
So the 3D geometry is basically showing us both the
Yes.
ground plane. It shows the feed,
Yes.
and also it shows the top patch.
This is our ground,
Yeah.
green one. This is our patch, and we can see this is our
So can you
feed.
zoom in? So
This is
you are
feed.
seeing the feed that is basically coming in
Yes.
from bottom upward.
Yes.
Okay, so let's go directly into the simulation now. So now knowing how to model this on a
Yes.
on a ITE 3D.
Yes.
So let's look at the simulation
So first
exam.
of all, we have to save this file. Save as just RMSA. Now, before simulation, this is a simulation.
Yeah. So there's a button.
So this is a meshing frequency. There are various parameters in this window.
Okay.
We have to set these parameters.
So what is the
before
frequency you are going to
So
simulate
we
this?
are going to 2.03
Okay,
gigahertz.
2.3
I already told. So meshing frequency tells us the highest frequency we are going to choose. So
Okay.
then
That's the lowest wavelength.
Yes.
And then you will know the
we
cells
can-
per wavelength.
Yes, cells per minute. So we can take it as a 3.
Yeah.
3
So you normally use a lambda by 20 in this case, or 20 cells per?
If it is a simple patch antenna, we generally take 30 cells per wavelength.
Okay.
And if it is a very complex structure like arrays of the patch, then we can think about less than 30 and 20.
So I think it's one thing that is important to explain here is, since we are doing a kind of a surface discretization, we can afford to have very fine grid.
Yes.
Whereas in the finite difference method, or finite element method, lambda by 20 or lambda by 30 is prohibitive. So you cannot simulate a bigger problem using such a fine grid.
Yes.
So in this case, we are going for lambda by 20 or lambda by 30. So it's because we are only interested in the surface aspect, and it's easier to do that. So it's not going to be very costly for simulation time.
There is another here. There is automatic edge cells.
Okay.
So it is always should be automatic AEC enabled.
Okay.
So that it automatically means the mesh size it automatically defines.
Okay. Okay.
At very means when there is a feed, it makes it fine.
Okay.
Fine meshing.
Okay.
When there is no changes, so then at that place it makes it coarser.
So what is important is the surface meshing also. We have to make sure that near the feeding area, the meshing should be fine enough to capture the resolution.
Yes.
Whereas in the outer areas, you can have a very coarse mesh.
Yes.
So that is what is being controlled by this particular parameter.
Yes.
And okay, so let's go forward.
Okay. Then next thing is we have to define the number of samples, of frequency samples at where this simulation software is going to simulate it.
Okay.
So we have to enter the number of points.
Yeah.
We can take it we can take it from 1.8 to 2.3 gigahertz.
So it's basically the frequency range that we are interested in.
Yes, range and the number of samples within this range.
Okay.
So let us take 501.
So we are taking 500 on one samples.
0.001 means at 1 megahertz. At every 1 megahertz, it will simulate.
Okay.
So it's okay. So these are the number of points at which this will.
So since it's a frequency domain approach, what we need to do is we need to simulate the same problem for different frequencies in order to get the broadband simulation of this particular patch antenna. So we are doing roughly 500 steps to do the entire simulation from 1.8 to 2.3. So roughly this is going to be 501 steps. That means doing the same simulation 501 times. Okay, let's go
at different points. Means it will simulate at 1.8.
Yes.
Another point 1.8.
Exactly. So it's there is a time stepping, or the frequency stepping. In this case is going to be roughly 1 megahertz.
Yes.
Right. 1 megahertz. Okay.
And if actually if we want to simulate it at every point 501 points, we have to select this.
Okay.
Means it will select all.
Yeah.
Otherwise, it will take random points.
Okay.
10 to 20 random points. It will select and automatically simulate it at that points only. So we are not going to take all these points.
For sure. Let's do now just for
the time.
Okay.
So next thing is we have to see the radiation pattern. So we have to select this tab so that a new window will appear. This will give us the radiation pattern at different angles. At theta is equal to 0 to 5 means again we are taking 37 samples.
Okay.
In the theta axis, and for phi axis we are taking 37 samples. So phi, as we know, phi varies from 0 to 360 degree.
So this is the entire circle.
At 10 degree, at every 10 degree we are taking one sample.
Okay.
In theta 0 to 180.
So this is basically this one. And then this one. So the theta is basically the one which is going to from top to this point. So it's a 180 degree angle. And what we are interested is also the circle, which is the 0 to 360 degree, which is the phi.
So we have taken in the theta direction, we have taken 37 samples. So every 5 degree angle.
Okay. So shall I ask you how we can do the antenna radiation now?
Yes. Just press OK. Okay. And then we can simulate it by pressing OK.
Okay.
Now it will take some time to simulate it.
So what is the rough time per discretization?
It depends upon the discretization and your
sample points.
Frequency samples and number of cells per wavelength and your computer means what we can say means your computer RAM or
okay. And normally what kind of methods you normally use other than method of moments for simulating this kind of patch antenna?
CST simulation software can also be used.
So this is a finite
integration technique.
Or also finite element methods do you use?
No,
we don't use.
Okay. FDTD method.
Yeah. So let's look into the simulation results itself.
So the simulation is over. We can see there is option of add graphs.
Okay.
So press click on this, and you can see there are various parameters: Y parameters, Z parameters, S parameters, Smith chart, and VSW. Firstly, we have to see S parameters. So we can select this S parameter, then press OK. Then we can see the S parameter magnitude, angle, real.
So let's look into the
decibel part. Then press OK. Next thing we can see the Smith chart also. Add graph, Smith chart. Press then OK.
And then radiation pattern.
Then radiation pattern we have to define separately. So
okay.
Next is VSWR. Okay. You can see also the VSWR. So now close this window. Yeah. We will see.
So now we are plotting the S parameter here. So the x-axis defines the frequency. So we are going from 1.8 to
2.3.
So 2.3, and similarly the y-axis is represented in decibel. So we are computing the S11 parameter.
Yes.
So let's see what the result says.
So we can see we are getting a very minus 35 dB at a frequency 2.02 gigahertz.
Okay.
So we started the antenna at 2.03 gigahertz. We have used the formulas available in the literature.
Yeah.
Based on formulas, we have decided the length and the width of and the other parameters. And based on that, we got at 2.0211 gigahertz.
Okay.
So, and next thing we can see the minus 10. Generally, in the antenna, we discuss about the bandwidth, impedance bandwidth.
Yeah.
For VSWR2 or S11 is less than minus 10 dB. So we can see the bandwidth of this antenna for minus 10 dB is from we can see in this window
from
2.006 to 2.03 gigahertz.
So it's quite a different range.
Yes. So we can calculate the difference.
So this is roughly
around 30 megahertz or
around 30 megahertz.
30 megahertz.
Okay. So as we can see in this particular S parameter, we are seeing for the minus 10 dB. So we are having roughly
30 megahertz.
So 30 megahertz. So this is the kind of range what we are getting for the S11 parameter. So if you want to improve this one, what you're saying is we can go with a different kind of material, which will have a different loss tangent. So this will increase the S11 bandwidth. Okay, so what normally is the application? You said that even though the loss tangent in this case is quite different, and it gives us 30 megahertz, it behaves better?
Yes.
Okay.
In this case, it has been observed also, as you increase the dielectric constant, because FR4 have more dielectric constant compared to this Arlon substrate.
Yeah.
So as we increase the epsilon r, generally the bandwidth decreases.
Okay.
As we increase epsilon r. And bandwidth also depends upon the thickness also.
Okay.
But here we have taken the same thickness.
Yeah.
We are varying only the epsilon r and loss tangent.
Okay. So basically, this is this is going into the basic electromagnetic theory of modeling antennas.
Yes.
From the methodological point of view, you have used the method of moments to compute this one, and you also explained we are taking 501 points, whereas what we see here is not 501 points. It's randomly choosing some points. And again, you explained us different materials, how you can improve the S11 parameter, or the minus 10 dB loss aspect of the antenna itself. So can we now look into the method itself and see how the accuracy of the method is going to impact how you can see the parameters that you're extracting in terms of accuracy? So maybe you can explain us that with the radiation pattern itself.
Yes. So next we can show you the radiation pattern. This is a window.
Yeah.
So in this we can see a 3D radiation pattern and 2D radiation.
Okay.
Pattern. Firstly we will see a 3D radiation pattern. So new window will appear.
Yeah.
From here you can see this is our
ground plane.
Patch.
Okay.
Ground plane.
So basically you have the ground plane. Yes. Can you zoom it in so that we can have a look? So what you have is a ground plane.
This is a ground plane.
And then you have a patch here.
And Now you can see this is our radiation pattern at a frequency of 1.8 gigahertz.
Okay, this is the lower frequency range we are looking into.
We can shift to the next frequency by pressing N. So we can see at 1.9 to 5 gigahertz. We can see all it is a red, means this is a scale.
Yeah.
Red, we have a maximum value of the electric.
So this is a dBi value you are computing.
Yes.
And it's a maximum gain that you are having. So if
resonating.
you go higher up in the frequency,
so at 2.015,
yeah,
you can see this, and this is 2.021 gigahertz, 2.05.
Yeah.
So
then the gain starts to decrease again. So initially the gain is low at certain lower frequency.
We can also see it's gain plot.
So it's basically going to change, and then at some point the maximum gain is appearing for certain frequency.
Yes.
So
at which it is resonating.
Exactly. Initially we said that we are going to choose lambda by 30, and what is interesting for us to know is in the method of moments, how do you understand whether the discretization what you're using is good enough to resolve the problem in an accurate way. So how do you normally do it as an engineer who is designing this antenna?
As we are using i3D software, we are not using any numerical technique.
Yeah.
Here we are using experiment. It's just a simulation.
So you use a thumb figure.
Yes, we are using a thumb rule. Just we are doing the simulation at 30 cells per wavelength, and again we are doing simulation at 35 cells per wavelength.
Okay.
We are comparing the results.
Okay.
If there is not a large difference,
yeah,
then we can see a lambda by 30 means 30 cells per wavelength can be used.
Okay. So basically
these are optimized for our antenna.
Okay. So it's a kind of a thumb figure, like as in practical experience shows you that if you start with the 35 cells per wavelength and you try to increase it to 40 cells or you're going down, then basically the result itself will show whether it's enough cells are there for the problem to be resolved using method of moments.
Yes.
So thanks a lot, Hemant Kumar. So you have done an excellent job in explaining us and also to the students how you can model such a patch antenna using method of moments. And it's the examples are very good. And thank you for your time.
Thank you.
Thank you.